Okay, then, well, thank you. See you a bit later. Ni hao. Professor Wang, thank you very much for that lovely introduction. Xie. I've chosen this morning to talk to you about the way in which physiology can be reintegrated with one of the mainstreams of biology, that is the theory of evolution, because I believe that one of the major changes in the conceptual foundations of biology are occurring in the field of evolutionary biology. Moreover, those changes are occurring in a direction that will enable physiology to become more relevant. Just a little bit of brief history, though. If you go back about 200 years to Jean-Baptiste Lamarck, the French biologist who published the Zoologie philosophique, he established the transformation of species. It's also well known that he assumed in his work that there could be the inheritance of acquired characteristics, and for that reason that process is sometimes called Lamarckism. But he didn't invent the idea. He assumed it, as others did too, from time immemorial, and in particular Charles Darwin, who 50 years later published The Origin of Species and proposed the theory of natural selection. He also assumed the existence of inheritance of acquired characteristics. The significance of this will become later in the lecture. And then around 1900, there was the integration of Mendelian inheritance, that is discrete inheritance, with evolutionary theory. And about the same time too, Weizmann established what was called the Weizmann barrier, the idea that the germ cells and their genetic material is not in any way influenced by the organism itself or by the environment. And then, something like 40 years later, a variety of people, Julian Huxley, R.A. Fisher, Haldane and Wright, put things together to call it the modern synthesis. So what exactly is the modern synthesis? It's sometimes called neo-Darwinism, and it was popularized in the book by Richard Dawkins, The Selfish Gene, in 1976. Its main assumptions are, first of all, that it is a gene-centered view of natural selection. The process of evolution, therefore, can be characterized entirely by what is happening to the genome. It would be a process in which there would be accumulation of random mutations followed by selection. Now, an important point to make here is if that process is genuinely random, then there is nothing that physiology, there's nothing that people like you and me can say about that process. That's a very important point. The second aspect of neo-Darwinism was the impossibility of the inheritance of acquired characteristics. It was miscalled Lamarckism. As I said earlier on, Lamarck did not invent the idea, he assumed it. And there is a very important distinction, particularly in Dawkins' book, The Selfish Gene, between the replicator, that is the genes, and the vehicle that carries the replicator, that is the organism or phenotype. And of course that idea was not only buttressed and supported by the Weizmann barrier idea, but also later on by the central dogma of molecular biology. All of these rules have been broken, and that is the subject of my lecture. First of all, are mutations random? A very important book to catch up with what is happening very rapidly in the field of evolutionary biology is the book by the Chicago biochemist James Shapiro, Evolution, A View from the 21st Century. He writes, and he gives detailed evidence, he has thousands of references on this in his website. It is difficult, if not impossible, to find a genome change operator that is truly random in its action within the DNA of the cell. All careful studies of mutagenesis find statistically significant non-random patterns of change. In other words, there are hotspots in the genome. Moreover, as we will see later on, the frequency with which those changes can occur can respond to what the organism is doing and what its environment is doing.